Good afternoon. Welcome to Fenix Infrastructure Webinar. Today, we have here with us Ramon Brasser from Research Center for Astronomy and Earth Sciences. Ramon will talk about planet formation simulations on JUSUF. And I'd like to remember you that this webinar is being recorded. And remind you that if you want to access the Fenix services, you can go all information on Fenix website. So we can access the Fenix service through Fenix website. And we have a white paper that was published on March, and I will share with you in the chat the link to access it. If you want to know more about Fenix, we can find this information on Fenix website too. If you want to make any questions, please wait until the end of the Ramon presentation, and you can use the chat or the QA options to make your questions. So Ramon, I pass the mic to you.
Okay, yeah. Very good. So welcome everybody to my presentation, this webinar for using Fenix resources. I'm Ramon Brasser. I am based at the Research Center for Astronomy and Earth Sciences in Budapest in Hungary, and I work in planetary science. So I was requested to give a webinar about using the Fenix resources, or in this case, the supercomputer that I've been requesting access to, and to basically tell you about how I use it and what I'm using it for. This presentation will be mostly scientific because in this webinar series, there is another talk about how to use the resources at, for example, the JUSUF cluster, or the one in France, or the one in Barcelona at BSC. So I do not feel that I really need to get into that. And I will give an overview of the kind of science that I do, and then I will branch into why we need HPC systems, not only me, but also other people in this field, specifically because of GPU computing. So for those of you who are not familiar with planetary science, so we are part of the solar system. So this is an image to scale in terms of the diameters or radii of the planets, but not their distance to the sun. So we are here on this small bluish planet with the moon, Venus, Mercury, Mars. Then we have Jupiter with its 4 Galilean moons. We have Saturn, the ringed planet with its moons, and Titan, the 2 ice giants, Uranus and Neptune, and then we have the Kuiper Belt and other material beyond Neptune. What is characteristic of the solar system is that we have 4 small rocky planets fairly close to the sun, within 1.5 AU, astronomical unit, which is the Earth-Sun distance. And then we have 4 large planets, 2 gas giants and 2 ice giants, which are further out, situated between 5 to 30 AU. So how did this come to be? And how did it come to be? Of course, the solar system is just one example of a multitude of planetary systems that we know today. I am mostly focused on the solar system, but I also will show some studies that I have performed for trying to form exoplanetary systems, but mostly it will be about this stuff here. So very briefly, for the non-initiated, the solar system formed about 4.6 billion years ago. We know this from radioactive decay of isotopes of uranium, thorium, and other long-lived nuclides, and then we can get absolute ages for things like meteorites, and then we know that the solar system formed about 4.6 billion years ago. From a cloud of gas that was eventually compressed under its own gravity, and in order to preserve angular momentum, which is a measure of the amount of rotation that you have in the cloud, you end up with a central blob and a disk spinning around it. This is like a pizza. So imagine that you are in a proper pizza restaurant and you have the chef having dough on his hand, and then he starts spinning it on his hand, and then the disk seems to spread. The pizza gets larger and thinner. That is the sort of mechanism that is at play here, where the star is the hand and then the disk is spinning around the star. It's not quite that way, but that's a rough way to imagine the process. And from that disk of gas and dust that is circulating the star, you are eventually able to form planets through coagulation and gas accretion and so forth. Giant collisions that are happening between small bodies like asteroids, bodies the size of the moon, Mercury, Mars, and eventually we end up with Earth-sized planets, while in the outer solar system, the process is not as well known, but we believe that you also form some very Earth-like planet that then eventually accretes the gas in the surrounding from this particular disk. There's a question in the chat. Okay. So this is a very rough overview of how the solar system came to be, but of course the angel is in the details. So we want to focus on the details, and that is where people like me come in. An overview of planet formation together with star formation, which I don't do, but of course they should be studied in tandem, is that we know from the solar system and from the thousands of other planets that we have observed around other stars that today roughly 15% of the planets that we have discovered are of the gas giant variety. So Jupiter or Saturn planets. And we also know that if you have large planets like Jupiter, you can either have a case where all those gas giants are nice and quiet, so they remain on nearly circular orbits and they do not disturb each other, they leave each other alone, like in the solar system, which is about a 10% chance. But 90% of the cases, these gas giants are too close for comfort, and they start to disturb each other, and then eventually they start crossing each other's orbit, right? Because the perturbations build up over time. They begin to scatter it one another, and of course, it's survival of the fittest. So the largest planet typically remains on an elongated orbit, and it knocks out orbits. So this planetary system, HD 67167, the planet orbits the star on a very elongated orbit that gets it as close as Mercury and further than Mars, and it's about a Jupiter mass planet. And that eccentricity, that highly elongated orbit, is probably the result of that planet throwing out other planets in the very distant past. But in 85% of the cases we have observed so far, we do not get gas giants. And then we typically end up with rocky planets. So for example, the solar system is one of them. But what we also find is that there are many planetary systems which are entirely inside the orbit of Mercury. So Kepler-11 is one of the first ones published back in 2010, 2009 even, when the Kepler satellite had just began flying, and that is 6 planets entirely within the orbit of Mercury. So these planets are very close together and they're very hot. Right, so this is a solar system-like analog. We call this angry gas giants, and these are hot super Earths. And the question, of course, is how do these kind of systems come to be? Rocky planet formation, or so scientists, there's no consensus among this, but this is roughly where things are going, is that you start with a disk, like this pizza-like disk around the star. Then you have initial coagulation of clumps of dust and micro-sized particles which are clinging together through electrostatic and gravitational forces, forming asteroids or planetesimals about 10 kilometers in diameter, maybe 100 kilometers in about 10,000 to 100,000 years. Then you get a phase of runaway growth, which is, again, survival of the fittest. So the largest bodies start to accrete the smaller ones. They compete with each other, and you end up with an oligarchy because you have a few big ones and all the other ones are gone. and that happens in about 100,000 years. You get Mars-sized bodies in about a few million years. The gas typically goes away after 5 million years. And then you have late-stage collisions in which these Mars-sized planetary embryos, as we call them, or just embryos for short, protoplanets is another term you can say, they then collide together in about 10 million to 100 million years. And one piece of evidence for this is the moon. The moon is about 60 million years younger than the age of the solar system. And it seems that the moon probably formed from a very large collision between the Earth and a Mars-sized planet, which then flung debris in a disk around the Earth. That material then collided and stuck together to form. Again, in a nutshell, so this is a long-term process. So the terrestrial planets form in about 30 to 100 million years, which is a very long time. But of course, it's very short compared to the age of the solar system. And the earlier phases happen much more rapidly. So the idea then becomes to be able to either model this or to be able to reproduce it and verify whether or not this is the case, whether these timescales make sense, or whether we are missing something and we need to go back to the drawing board. So when I was speaking about a system like Kepler-11, where you have so many planets inside the orbit of Mercury, the question that planetary scientists like me ask ourselves, do these planets actually form there where they are located, this close to the star? Or do they actually form much further out? And then because of interaction with the gas disk, which gives them a headwind, they then spiral towards the star. Very slowly, their orbit shrinks and eventually they end up very close to the star. So here is an example of a simulation. There will be many of these in this presentation. This one was not run by me. This was graciously donated to me by a colleague, in which they studied the formation of a compact system like Kepler-11. So this is the horizontal axis is what is called the semi-major axis of the ellipse. So it's the orbit. So it's like a measure of how large the orbit is, how far the body is from the star. And this is the eccentricity, so how elongated the orbit is. 0 is a perfect circle, 1 is a straight line, and 0.1 is like a mild eccentricity. So I'm going to play this for you. And this is an example of local formation. So I start with bodies, some large bodies, which are the large circles, and a lot of small bodies as well. And we watch what happens. So you can see that very, very quickly, these bodies collide. We assume perfect accretion, which is not always correct. But implementing non-perfect accretion is computationally difficult and expensive. So we prefer to kick the can down the road and do it later. But you can see that even in something like a million years or a few thousand years, I am already starting to form planets. Now, this is difficult because geochemical and geodynamical constraints make it very difficult to reconcile forming a planet in a few thousand years with the chemistry of it. But anyway, I mean, that is the kind of simulations we were able to do until recently. In terms of the solar system, usually what has been done is that people adhere to what is called the classical model. So we start with Jupiter at about 5.2 AU. That's where it is today. So this is 1 AU is the Earth-Sun distance. And we start with a disk only consisting of small bodies. Right? There's no gas, there's nothing. We just want to see what, if we plug this into the computer, what kind of thing do we get? And is it a good proxy for being able to form the terrestrial planets? And the closer you are to the star, the drier you are expected to be. So these red planetesimals are mostly expected to be completely dried out. These ones have a little bit of water, and these have got some more water. Right? So remember that. And as I start the simulation, you see that very close to the sun, the growth is quicker than farther away, and that these bodies are mostly red. But now they start to actually change color. So they started as red when they were growing, but the larger they grow, the bluer they become. And the reason for this difference is that they are not only absorbing material that is right next to them in their very close proximity, but they are also starting to absorb material from much farther out. And the reason for this is that Jupiter is also disturbing this whole region here. And that causes then larger bodies are starting to grow. That causes mixing in the disk. You have gravitational encounters between the smaller and the larger bodies. The larger bodies put the smaller bodies on different orbits, and stuff is basically being tossed all around over the place. I'll play it again. So Jupiter ticks this stuff here. You see local accretion mostly happening in this region here. And then eventually the orange and the blue and the red, they get all mixed together because of the gravitational stirring and the encounters and everything. And that happens on about a 20 to 30, 50 million year time scale. So these three planets here, this one stays red most time. It just ate the blue body. So now it has a little bit of water, but not much. And eventually we end up with something like this. So we have three planets in this particular case. You can never reproduce the system as a whole. I'll get to that in a tick. But you see that they're somewhat blue. So they have absorbed some stuff from the outside and most of the stuff from the inside. So does this represent the solar system? No, but if you maybe run a few of these, you might get lucky. So this leads me to the first problem in planet formation, and it's one of the reasons why we need supercomputers like the ones that Fenix provides for us in Germany, in France, in Italy, in Spain, and in some other places as well. The reason is that the simulations are chaotic. Chaotic, I don't mean that essentially the system goes completely berserk. It just means that if I start with the same initial conditions, but I have something a little bit different, and the outcome after a long enough time becomes completely unpredictable. So here's an animation of a disk of planetesimals in the top and in the bottom panel, and they are essentially the same initial conditions, right? It's all, there's only a tiny little bit difference between them. So this is being sped up, and we are now tracing the orbits of all the stuff as it is colliding together and as things are moving around. It's not the same kind of animation that I showed before, but this actually really shows the chaoticity of the system. So you can see that close to both stars, I'm starting to have a few orbits there. You saw a wave propagating, so that means that there was some shock in the system, like two bodies colliding or whatever. I'm starting to also get more eccentric orbits. There's stuff colliding closer to the star, while farther out, things take more time because the orbital period is longer. And eventually, the system will start to calm down because most debris has been swept up by the larger bodies that have formed. And with time, you know, as things continue to settle down, we have fewer and fewer bodies, again, because they have nowhere to go but to collide with the planets. And eventually we end up with two different planetary systems. Even though the initial conditions are almost the same, we end up with two different systems. And then, of course, you can say, well, hang on, so how do we know which one is correct? And the question is, they're both correct. So here I have three planets, here I have three smaller planets, and I have another one that is going around somewhere here. Both are correct, according to the model, but whether they comport with the systems that we observe, that is another matter. But it shows you that if I run just one simulation and I get some outcome, that is not sufficient. We need to run many simulations to apply statistics and then get a statistical distribution of outcomes and see whether those comport with the planetary systems that we see. That's why we need HPC resources, because they have many GPUs and CPUs available that we can use if we apply for enough time and, of course, get the time. The second problem that we run into is what is called the n squared problem. So if you have n gravitationally interacting bodies, then the number of force calculations that you need to do goes as n squared. So you double the number of bodies, you need to do 4 times as many operations. this eventually becomes a problem. Now, there are codes like a tree code which will approximate this with an n log n, so it increases slightly slower than linear, but they are approximations and they're not accurate enough for the kind of simulations that we want to do. So on a regular CPU, the core operations are in sequence. So the time to complete the simulation increases as n squared, because you have to do a double loop. You have to go from one particle and then for all the other particles, the next particle, all the remaining particles, the third particle, all the remaining particles after that. And you can program it in something like a double do loop. But the CPU needs to do this part and then go to the next step and then iterate this, go to the next one and iterate all of that again, which takes an enormous amount of time. So on a modern CPU, you can do about 1 to 200,000 integrations per particle per second, right? So if you need to do 10 to the 10 time steps, like for example, for terrestrial planet formation, with 2,000 self-gravitating particles, assuming that none of them go away, it will take 8 years for one simulation to finish, which of course is ridiculous, right? So we need something that is better. And that is where the graphics cards start to come in. But before I get there, one way we can speed things up is parallelization. So instead of using one CPU core, you can say, well, I'm going to spread the load over multiple CPU cores. For example, with OpenMP, and I just use one node. With MPI, you can use multiple nodes, but then you're running into all sorts of other problems. So the number of CPU cores that you use then is able to speed things up. So if I have one core, I use an enormous amount of energy and a lot of time. But if I use 4 or 8 or 16 or even 64 cores, I might be able to speed things up. Of course, there is a limit to how far you can go because of Amdahl's law and other things that cannot really be optimized. And it turns out that for the kind of problems that I study, it flattens off between 32 to 64 CPU cores. So you can run 1 or 4 simulations on one node on JUSUF, for example, the German supercomputer that I use in this particular example. And then the language that you write your code in is also important. If you write it in Python, which is not really optimized for numerics, although with NumPy, of course, things are a lot better, then it is much slower than if you write it in C++ or Fortran, right? And then CUDA, which is the language where graphics cards can even be more optimized because it is more hardware specific. And of course, all of this is then important in terms of energy usage, how much time you need to apply for on the supercomputer and so forth. And all of this, and how many CPU cores you need, and all of this is then tied together. But can we do even better than just using a high number of CPU cores? And the answer is yes. And that is where graphics cards come in. So enter GPU computing, graphical purpose computing. It is a massively parallel infrastructure with enormous computational power. So the top of the line GPU is the NVIDIA A100, which costs about 10,000 euros each. And it has a peak performance of almost 10 teraflops in double precision. FP64 is double precision, 16 digits. While an AMD EPYC 64-core CPU has about a third of that in double precision. So if you look at this figure here, this is on the horizontal axis is the number of self-gravitating bodies that we have tested. And on the vertical axis is the number of steps per second per particle. Okay? That seems like a little bit of an abstract concept, but if you think about it, it really allows you to predict and estimate roughly how fast your code is going. So for the A100 GPU, which is this purple line here, I can get a maximum performance with about 8,000 self-gravitating bodies. I can get 2.5 million steps per particle per second. Right. So then then I can divide this by the number of particles, and I then know how many steps per second I do. And then if I say, okay, I need to perform this many steps, assuming no loss, I have some idea of how long the computation is going to take. And this ramp down beyond about 32,000 planetesimals is because of the n squared thing, is that essentially you're using up all the computational power of the GPU. And if you add more particles, essentially not everything can be computed at the same time. So the GPU needs to wait and do one batch and then the next batch and then the next batch. And of course, if you increase the number of particles, then you're going to have to wait twice as long because of the n squared problem. Right? And then this slowdown here is because of the way the code that we use is written, is that you have some overhead here. So it's most optimized here. But for example, you can also say, well, these A100 cards are a bit expensive. So I'm just going to use the kind of graphics cards you get in your desktop computer, right? The ATX, the RTX and the GTX cards. And they are plotted here. So you can see that they are much slower in terms of computation than these top-of-the-line P100 and A100 cards. That is because they're double precision truncated. If you don't do that, you can get a higher performance, but at the expense of accuracy. It still works. It's still great compared to a CPU, but it's not as great. So GPU computing is the fastest option for high-end. And this is exactly why we need to have HPC resources, because this is the future for terrestrial planet formation simulations, the way that I'm doing it and some of my colleagues as well, because we have so much computational power available in one card, and it doesn't use insane amounts of electricity either. So why do we require HPC resources? Right? I cannot do my work in a reasonable amount of time without these resources being available. So of course, one thing is that these GPUs are extremely expensive. So if I want to build a cluster with, let's say, 10 of these cards, that's 100,000 euros just for the cards. Then I don't have the computers and I don't have the electricity and I don't have all the other infrastructure. So you're looking at, you know, at least $250,000 just starting, and then you only have 10 cards, right? And if I need to run many simulations for statistical purposes, for example, I need to run 30 or 40 of these, then, you know, I have to, even with 10 cards, I'm still going to have to wait almost a year, because each simulation takes about 1 to 2 months. So if for a person like me who really has to do these statistical analyses and wants to push the simulations to the limit by using more planetesimals to resolve things like forming small planets the size of Mars, then GPU computing, as provided by HPC resources like Fenix, is the way to go. And just to give you an example, let's say I start with 16,000 self-gravitating planetesimals. Then the A100 can do about 183 steps per second, while the CPU can only do 8. So I can finish in about 2 months. Usually it's quicker because I lose planetesimals. It's about a factor of 2 less. So I can finish in 1 to 2 months. But on the CPU, it will take a very, very long time, even using 8, 16, or sometimes even 32 cores. So it just becomes unfeasible. There's no panel that will give me HPC resources when I say I need 3 years to run these simulations still, so you're out of your mind. You have to try something else. So GPU is the way to go. The code that I have been using is developed by Simon Grimm at the University of Bern, he's now in Zurich. And it's an open source and GPU and body grade integrator specifically tailored for planetary problems. So it can be downloaded from here. The slides will be shared, and for people that see this webinar later, they can just look at the link and type it in their browser. It requires an NVIDIA GPU to run, although we can now run on AMD GPUs with HIP, but it is not as fast as on the NVIDIA cards because there is no specific language for AMD GPUs. And we usually run 1 simulation per GPU. It can be very easily compiled. You don't need specific libraries or all sorts of other things. Just you need CUDA version 10 or higher, 1 NVCC command, and you're golden. There is a CPU-only version in the making, which we're testing right now. There is a multi-GPU version as well, but it doesn't give so many benefits, so that's kind of stalled. And you don't need any specific HPC resources. You don't need to load all sorts of modules and so forth in upon compiling or when you run your Slurm script. You basically just tell this, put in the usual parameters in your submission script. You just give it the executable to run that is compiled on the master node or whatever, and it runs. In that sense, it is extremely user-friendly. And there's ample documentation on this website with how the setup, how the input files are structured, what the parameters are, what it can and cannot do. And for those that are really interested, I encourage you to check out this publication that we wrote last year in the Astrophysical Journal. That describes the Ganga code and all of the things that it can do as a state of the art. So the kind of problems I would like to solve, for example, using JUSUF and Fenix resources, is terrestrial planet formation in the solar system. What are the timescales? What is the distribution of outcomes? What are the other orbital parameters that we see? Giant planet migration. So the giant planets today are fairly well separated. And the idea is that they formed closer together about 4.5 billion years ago. There is ample evidence from the orbit of Pluto, from the Kuiper belt beyond Neptune, that the giant planets migrated outward. So they didn't form where they were today, but they were closer together and then expanded. I'll show you this later. Giant planet formation. Why are Jupiter and Saturn so much bigger than Uranus and Neptune? Why is Jupiter 3 times as massive as Saturn? On what time scale did the giant planets? Was it 1 million years? Was it 10 million years? Something called late accretion. So if you have a golden watch, right, the gold is not supposed to exist in the Earth's crust because it is what is called a highly siderophile element. So it should be in the Earth's core, but not in the crust or in the mantle, yet it is there. And the idea is that it essentially came after the Earth mostly formed. It came from impacts that left some gold in the crust, and that's why we can mine it. That is called late accretion. Right, so it's basically the leftover bombardment onto the terrestrial planets after the terrestrial planets and the moon had already formed. But it also happens in the outer solar system. The satellites of the giant planets all have craters. Right, the moon has craters, Mars is cratered, Mercury is heavily cratered. So on what time scale did that happen? How high are the crater densities and so forth? And rocky exoplanet formation. So that Kepler-11 system that I showed, but there are so many of these compact systems, but how do they form? To be honest, we don't yet know. There are ideas out there that tell us, well, it has to be either this or that, but we don't really know. So this is something that we hope to be able to do in the future. So here is a snapshot of Gengar in operation. This was not run in JUSUF, but the results will be very similar. So if I start with 2048 self-gravitating planetesimals, and after 1.5 billion years, I have about 3 planets. And I can do this for more objects, and eventually you see that the outcome is always different. None of these systems are actually the same. Now, the question is, of course, you can say, well, that's because you have a different number of planetesimals. Maybe, but if I were to run 10 of these or 10 of each one of them, they would still look different because the system is chaotic. So, one of the things we would like to know is if you keep increasing the number of bodies, do you saturate at some point where you say, well, the outcomes are statistically indistinguishable if I use this number of particles, or if I have twice as many or half the number of particles as that? We don't know. This is one thing we would like to test, but it seems from this that maybe it could be the case that you already start to saturate at 8,000 planetesimals. We don't know. So this is something that we are working on. Here are 2 animations that I will start that was run by my former student, Jason Wu, on the V100 GPU, which is the previous generation. We start with 40,000 planetesimals, all of the same diameter, the same mass. This is eccentricity versus semi-major axis, which I explained earlier. Inclination is essentially how tilted the orbit is with respect to some reference plane, which is usually the ecliptic. Or where the plane in which all the orbits of the planets are situated. This is the radius, and this is the mass of these planetesimals. Again, all as a function of semi-major axis. And in this case, Jupiter and Saturn are on eccentric orbits like they are today. And in this case, Jupiter and Saturn are on circular orbits. Again, that is a result of several models and several theories that have been in the past that maybe Jupiter and Saturn formed on circular orbits and they gained their eccentricities later. There's a lot of research that suggests that that's the case, but here I show both. So off we go. And you see that close to the inner edge, I start to form Mars-sized objects roughly, within, let's say, 1.5 to 2 million years. And all of these objects are nicely together. I even have lunar-sized objects because the moon is about 10 to the -2 Earth masses, and I have that. This phenomenon here, basically you see that objects are starting to get a very high eccentricity and then they damp down. This is because essentially the whole asteroid belt region is emptied out by the perturbations from Jupiter because of its eccentricity. So in this particular simulation here on the left, I end up with an almost empty asteroid belt. And I start to form mostly Mars-sized objects, which eventually will start to collide together. While on the right-hand side, I do not have this emptying out of the asteroid belt. So I'm slowly starting to accrete some lunar-sized objects around 2 to 2.5 AU. And of course, those of you that know a little bit about planetary science will say, well, Ramon, this is nonsense because we don't have these kind of bodies in the asteroid belt. And I say, you're absolutely right. So something must have emptied out the asteroid belt if these initial conditions were correct, which of course is a whole other question that hopefully we will be able to solve. This one finished earlier, but you can see now that after about 40 million years, I end up with one Earth-sized planet, a Venus-sized, and then some material here closer to Mercury. I have something that is a little bit larger than Mars here. So this simulation is fairly successful. We have more or less the distribution that we want. And we are left with a lot of material here, which is then the feeding stocks for late accretion. So we started with 40,000 planetesimals. We end up with a few hundred at the end. And this kind of simulation can be done on GPU in about 2 months. So with the eccentric Jupiter and Saturn, we can more or less get Earth and Venus, and we can get small Marses. But with the circular Jupiter and Saturn, we cannot. So we need to have some sort of trigger that will have these Mars-sized bodies collide to form Venus and the Earth. So let's now look at something that I have actually run on JUSUF as part of my previous Phoenix proposal, which is to look at exoplanet formation. So in this case, I start with a disk and which also has gas in it, but the perturbations from the gas are mimicked as fictitious forces. And there are theories that tell us how that should happen in theory. So I start with a disk of material here with planetesimals or bodies with different sizes and masses, roughly between 0.2 and 2 AU. This started with about 28,000 planetesimals around a star with 0.7 solar masses, so it's slightly smaller than the Sun. It's called a K-dwarf in an attempt to form rocky exoplanets. And there's about 5 Earth masses of material in this disk. So you see that we quickly form a host of a convoy of these smaller bodies that are migrating inwards because the gas disk gives these planets a headwind, so they lose energy and angular momentum, and therefore they spiral towards the Sun. And the inner edge of the disk is about 0.1 AU, so that's where they stop. And then I end up with these bodies here, slightly eccentric, while in the outer part, of course, everything is slower. So I end up with more things still forming and colliding and scattering each other. And in this particular case, after about 10 million years, I only end up with bodies roughly the size of Mars. So it is difficult with these initial conditions to form planets that are heavier than Mars-sized planets. So Earth and super Earths, this model fails to do that. So we need to go back to the drawing board and either put in more mass or try to understand what else is happening. But on JUSUF, starting with 28,000 bodies, this takes about 40 days. So that then also gives me an idea what the speed of the hardware is. And then when I write proposals for time in the future, I say, okay, well, I need about 40 days for that many particles. So if I want to do, let's say, 50,000 particles, I need about 90 days. And if I want to run 100 simulations, then I need, 90,000 days worth of computing time on GPUs, which they will not give me, but that is the kind of calculation to do. Giant planet migration also run on JUSUF. This was more a test case to also peg how quick the hardware is, but this is an ongoing problem. I now start with 5 giant planets. One of them is tossed out. That is a theory that we have, and it gives better statistics. And I start with a disk of planetesimals beyond the outermost ICEI. So this planet will end up being Neptune, this one will end up being Uranus, and here in this region, I have 20 Earth masses of small bodies, right? So I just put this on JUSUF and we just watch what happens. So this planet moves into the disk. You can see, if I rewind it, you can actually see that this planet moves outward, right? Because it starts at about 22 AU, and by 6 million years, it's already at 28 AU, right? So this is because of angular momentum and energy conservation that this material, some of it gets thrown to the inner more planets, so it loses angular momentum and energy, and therefore this planet then has to gain angular momentum and energy, and it moves outward as a reaction to that. And these planetesimals get scattered all over the solar system because they constantly have encounters with the giant planets. The middle planet gets thrown out, and then eventually I end up with a solar system that is not playing anymore. But eventually I get Uranus at about 20 AU, Neptune at 30, and then Jupiter and Saturn at 5 and 10 AU, roughly where they should be today. And these planetesimals will decay on billion-year timescales. And this simulation takes about a week. Start with 30,000 planetesimals. So that's very good. And we can test various configurations of the planets to see which one best reproduces the solar system as we know it today. Not only the configuration of the planets themselves, but also the small bodies, because they have a particular distribution in semi-major axis, eccentricity, inclination that we can use to test models. And again, because the system is chaotic, no simulation's outcome is the same as the other. We need to run many of these for statistical analysis. The probability of getting a good solar system analog is about 5 to 10%. So we need to run 20 to 50 to 100 simulations at least. And with 7 days each, that is not too much time on JUSUF. This is an ongoing project, which is pushing the science further. So I take a snapshot of a terrestrial planet formation simulation that I showed you earlier with the 2 panels, the 2 simulations. And then on top of that, I want to have giant planet migration. So I start with 5 giant planets. I have the disk here, and this is a snapshot at 10 million years after a simulation that I ran earlier. This is also run on JUSUF. This takes about 3 weeks or something like that. You see that the giant planets have migrated, and some of that material here is being scattered, and some of that also ends up in the inner solar system. And the idea is that if we have, from the failed simulation that I showed you earlier on the right-hand side, where I only end up with Mars-sized objects, I said we need some sort of trigger to be able to get that stuff excited and then they start colliding with each other. Maybe giant planet migration will provide that trigger, because Jupiter and Saturn is so massive that anything that happens to them will affect the whole solar system. So if they become eccentric, or if they move, then everything is affected. And you can see now that I'm starting to get more and more planets here in the inner solar system. Instead of having 15 Mars-sized bodies, I now end up with 4 bodies that are roughly half an Earth mass. So it's still not great, but I feel that probably I am on the right track there. And again, because the system is chaotic, not only the giant planets, but also the terrestrial planets, I need to run many of these, so I need to have access to HPCs. That was my last slide, apart from this one. So the conclusions are that planet formation is a very thriving and dynamical field in planetary science and in astronomy. So there are many open problems, especially when it comes to the formation of exoplanets. So planets around other stars. There's many things we do not understand. So you know, if you're interested in this, then this is definitely something that may provide interesting returns. The models, the outcome of the simulations is always chaotic. So you need to run many simulations. And because of that problem, and also because of the n squared for the forces, we need to use GPU computing. And not only do we need GPU computing, we really need to have HPC resources available to us, because we need to use many GPUs at the same time. Of course, you need to spread it out a little bit. But if you only have 1 or 2 GPUs and you need to run 100 simulations that take 2 months, then you're basically waiting forever and you will never publish a paper. So you need a combination of availability, time, and resources, and then Fenix RI to the rescue. Okay, so this was my last slide, and I want to thank you for your attention.
Thank you very much, Ramon. It was so interesting, your presentation. So if someone wants to have to ask something or make your questions, please use the chat and the QA option on the downside of your screen. We have a question, Ramon.
In some of your simulations, you mentioned that some planets or informations are sent out of the solar system. Are you able to track their location afterwards? Is it something interesting or not? So when I say send out of the solar system, that means that they are ejected from the system. So they have their binding energy to the sun. For anything that is bound to the sun, the total energy is negative. And what you can do through repeated encounters with planets is you can give it enough energy that the energy becomes positive. And the velocity is higher than the escape velocity from the sun, so that the body will essentially be sent into space, and then it will orbit somewhere in the galaxy, in the Milky Way galaxy. So can we track that stuff? No, because we would then need to start modeling the galaxy on top of the system, which basically becomes unwieldy. What we tend to do is, usually in a simulation, we set some maximum distance and we say, okay, if a body is beyond that distance, we stop taking care of it. Now, if it's unbound, if it's hyperbolic, then of course it makes sense. For bound bodies, it is more difficult. There is something called the Oort comet cloud around the sun, in which you have comets which are residing on orbits about 10,000 times as far as the Earth. They're very weakly bound, but sending stuff to the Oort cloud and getting trapped there is like a 5% chance. So most stuff that ends up coming back and back, even on a very elongated orbit with thousands of AU, eventually will be ejected. I hope that answers your question. Is it easy to simulate the state of other galaxies considering their original stars? I do not know. I am not an expert on galaxy formation simulations. I do know that there are people that are doing this. For example, Joachim Stadel at the University of Zurich is the name that comes to mind. And they definitely use HPC resources because there's no other way to do this. But if you want to model planet formation within a galaxy, that becomes unwieldy, because the time step that you need to use to resolve the planetary system is less than a year, while orbiting the galactic center takes 200 million years. So the difference in timescales just makes it computationally impossible to do. So if you're interested in galaxy formation simulations, then you're not at the right address with me, but maybe that is something that can be discussed in these webinars in the future.
Any other? So we have the survey on your email and in the chat. And if you want to reach out a Fenix team, we can use one of our channels, Twitter, LinkedIn, website, or by mail too. And thank you very much for all of you that stay with us here today with Ramon Brasser. Ramon, thank you very much. We really appreciate your presentation and very interesting matter. Thank you.
There's one more question. I will answer it now. Just a comment on the last question. Ejected planets from forming planet systems is interesting in the sense that it can be compared with the observed free-floating planet population from micronauts. I completely agree. And that is indeed something that needs to be checked. To my knowledge, this is not an active topic of research. So if you're interested, I would say.
Yeah.
Okay.
Thank you very much.
Thank you.
It was a pleasure. Bye.